Imagine, if you will, standing in an open field on a clear night. Above you stretch countless stars, their light having travelled unimaginable distances to reach your eyes. What you cannot see, cannot feel, and cannot hear is the vast magnetic envelope that surrounds you and every living thing on Earth. This invisible force field extends far beyond our atmosphere, reaching tens of thousands of miles into space, deflecting the solar wind and cosmic radiation that would otherwise strip away our atmosphere, sterilize our world. The story of Earth's magnetic field begins in the deepest reaches of our planet, in a churning sea of molten iron nearly 3,000 miles beneath your feet. Here, in temperatures that rival the surface of the Sun, liquid metal flows in vast, complex currents driven by the rotation of our world and the slow cooling of the Earth's interior. These movements create electrical currents, and those currents generate the magnetic field that has shaped the course of life itself. But this tale extends far beyond the realm of physics and geology. It is a story woven through human history, from the first curious observations of ancient peoples who noticed that certain stones could attract iron, to the revolutionary moment when seafarers realized they could use these magnetic properties to navigate across vast oceans. It is a story written in the rocks of the ocean floor, where the magnetic signature of ancient fields lies preserved like pages in an enormous book, telling us of times when north became south and south became north, in a dance of magnetic chaos that has repeated itself throughout Earth's long history. Tonight we will explore how this invisible shield came to be, how it has changed over the eons, and what its future might hold. We will discover how the same force that guides a compass needle also paints the night sky with curtains of ethereal light, creating the aurora that has inspired wonder and mythology in cultures around the world. And we will contemplate what might happen if this protective field were to weaken or disappear entirely, as it has threatened to do before and surely will again. So let us begin this journey into the hidden history of Earth's magnetic field, starting with the earliest human encounters with this invisible force that would eventually change the course of civilization itself. The ancient discovery of magnetism, long before humans understood the true nature of magnetism, they encountered its mysterious power in the form of naturally occurring magnetic stones. These remarkable objects, which we now know as magnetite, seem to possess an almost magical ability to attract pieces of iron and steel. The ancient Greeks called these stones magnetes lithos, meaning the stone from Magnesia, named after the region in Asia Minor where they were commonly found. Picture, if you will, a shepherd in ancient Anatolia, perhaps 3,000 years ago, walking across the rocky hillsides with his iron-shod staff. Suddenly, his staff is pulled toward a dark, seemingly ordinary stone. When he bends to examine it, small pieces of iron filings from his tools seem to leap through the air, adhering to the stone's surface as if drawn by an invisible hand. This moment of wonder, repeated countless times across the ancient world, marked humanity's first encounter with the mysterious force we now call magnetism. The Chinese, with their keen observation of natural phenomena, were among the first to systematically study these magnetic stones. By the 1st century CE, they had discovered that when a piece of magnetite was suspended or floated on water, it would consistently orient itself in the same direction. This discovery led to the creation of the first magnetic compasses, though initially, these instruments were used not for navigation but for a practice the Chinese called feng shui, the art of harmonizing human habitation with the invisible forces of the natural world. These early Chinese compasses were crude by modern standards. A piece of magnetized iron, often shaped like a spoon or fish, would be placed on a smooth bronze plate marked with directional symbols. The magnetic spoon would slowly rotate until it pointed toward what the Chinese called the south-pointing direction. Interestingly, early Chinese compasses pointed south rather than north, reflecting a different cultural perspective on directional orientation, yet they were detecting the same invisible field that surrounds our planet. Today, the knowledge of magnetism spread slowly along the trade routes that connected the ancient world. Arab merchants and scholars encountered magnetic stones and compass technology during their travels to China, bringing this knowledge westward along the Silk Road. By the 11th century, descriptions of magnetic compasses appeared in Arabic texts, where they were described as essential tools for desert navigation, helping caravans maintain their bearing when the sun was obscured by sandstorms and the stars were hidden by clouds. In Europe, the magnetic compass arrived during the 12th century, probably brought by returning crusaders or introduced through trade with the Islamic world. The Europeans called the magnetized needle a lodestone, from the Old English lode, meaning way or course, recognizing its essential role in showing direction. European compass makers made several innovations, including mounting the magnetized needle on a pivot and marking it with directional points, creating the familiar compass rose that would become standard for Can-D, maritime navigation. But the mystery of why magnetite behaved as it did remained unexplained for centuries. Medieval scholars proposed various theories, from the supernatural to the philosophical. Some believed that magnetic stones contained a living spirit that yearned to return to the celestial sphere from which it came. Others suggested that the Earth itself possessed a soul, and that magnetic stones were drawn toward this planetary consciousness. The true breakthrough in understanding magnetism came in the 13th century through the work of Petrus Peregrinus, a French scholar who wrote the first systematic treatise on magnetism titled Epistole de Bekenner, Magnete. In this remarkable work, Peregrinus described detailed experiments with magnetic stones, including the discovery that magnets have two poles and that like poles repel while opposite poles attract. He was the first to use the terms North Pole and South Pole in reference to magnetism, establishing terminology that we still use today. Peregrinus made another crucial observation that would not be fully understood for centuries. He noticed that no matter how many times you broke a magnet into pieces, each fragment would still possess both a north and south pole. This phenomenon, which we now understand in terms of magnetic domains and atomic structure, suggested that magnetism was a fundamental property of matter itself, rather than something that could be isolated, extracted. The medieval period also saw the development of increasingly sophisticated compass designs. Italian compass makers in the port cities of Genoa and Amalfi created instruments that could function reliably aboard ships, using gimbals to keep the compass level despite the rolling motion of a vessel. These maritime compasses typically featured a magnetized needle attached to a circular card marked with 32 directional points, allowing navigators to determine their heading with remarkable precision. As compass use spread throughout the maritime nations of Europe, navigators began to notice something puzzling. The compass needle did not point to true north direction of the North Pole, but rather to a point somewhat east or west of true north, depending on where they were located. This angular difference, which we now call magnetic declination, varied from place to place and seemed to change slowly over time. This discovery led to one of the first hints that Earth's magnetic field was far more complex than anyone had imagined. The realization that magnetic north and true north were not the same location suggested that the source of the Earth's magnetism was not simply a giant lodestone buried at the North Pole, as some had theorized, but something far more dynamic and mysterious. Portuguese and Spanish navigators, pushing into previously unexplored waters during the Age of Exploration, carefully documented these magnetic variations. They created charts showing lines of equal magnetic declination, called isogonic lines, which revealed that Earth's magnetic field formed a complex three-dimensional pattern that wrapped around the entire planet. These observations would prove crucial for later scientists attempting to understand the true nature of Earth's magnetic field. The compass revolution transformed human civilization in ways that are difficult to overstate. Before reliable magnetic navigation, sailors were largely confined to coastal waters or short trips across familiar bodies of water. The compass opened the world's oceans to exploration, enabling the voyages of discovery that connected previously isolated continents and changed the course of human history. But even as the compass proved its practical value, the fundamental mystery of Earth's magnetism remained unsolved. Why did the planet behave like a giant magnet? What force deep within the Earth created this invisible field that could guide a tiny needle? And why did this field seem to shift and change over time, as if driven by some vast unseen engine in the depths of our world? These questions would occupy some of humanity's greatest scientific minds for centuries to come, leading to discoveries that would revolutionize our understanding not only of magnetism but of the Earth itself. The birth of Earth's magnetic field. To understand the origin of Earth's magnetic field, we must journey deep into our planet's interior, to realms where temperatures soar beyond the melting point of iron and pressures reach millions of times that of our surface atmosphere. Here, in the metallic heart of our world, lies the engine that has been generating Earth's protective magnetic shield for billions of years. The story begins with the formation of Earth itself, some 4.5 billion years ago. In the early solar system, countless rocky and metallic fragments orbited our young sun, gradually colliding and accreting to form the planets. As Earth grew larger through these cosmic impacts, the tremendous energy released by each collision heated our falling world to temperatures that melted rock and metal alike. During this violent period of planetary formation, the heaviest materials, primarily iron and nickel, sank toward the center of the molten Earth under the influence of gravity. This process, known as planetary differentiation, separated our world into distinct layers. A rocky outer shell that would eventually become the crust and mantle, surrounding a dense metallic core composed primarily of iron with smaller amounts of nickel and other heavy elements. As Earth continued to cool over millions of years, the outer portions solidified into the rocky mantle and thin crustal layer we know today. But the core remained molten, kept liquid by the immense pressure and heat generated by radioactive decay of elements like uranium, thorium, and potassium scattered throughout Earth's interior. This liquid iron core, extending from about 1,800 miles below the surface to nearly 3,000 miles deep, forms the largest reservoir of molten metal in our solar system. But it is not simply the presence of liquid iron that creates Earth's magnetic field. After all, a stationary pool of molten metal, no matter how large, would not generate magnetism. The key to understanding Earth's magnetic field lies in recognizing that this vast iron sea is in constant motion, driven by forces that create complex swirling currents throughout the liquid core. The primary driving force behind these currents is Earth's rotation. As our planet spins on its axis once every 24 hours, the liquid iron in the core cannot rotate as a solid body. Instead, it experiences what physicists call the Coriolis effect, the same force that shapes the rotation of hurricanes and the circulation of ocean currents. This effect causes the flowing iron to twist and spiral as it moves, creating complex patterns of circulation that extend throughout the entire liquid core. But rotation alone would not be sufficient to generate a magnetic field. The second crucial ingredient is convection, the movement of hot material upward and cool material downward, driven by temperature differences within the core. The very center of Earth, at the boundary between the liquid outer core and solid inner core, is slightly hotter than the regions closer to the surface. This temperature difference, they're measured in hundreds rather than thousands of degrees, is enough to drive powerful convective currents throughout the liquid iron. Imagine, if you will, vast plumes of hot molten iron rising from the depths of the core, carrying their heat upward toward the mantle boundary some 1,500 miles above. As these iron currents rise, they gradually cool, eventually becoming dense enough to sink back toward the center of the Earth. This creates enormous convection cells, circulation patterns that dwarf any weather system on Earth's surface. These convective flows, twisted by the planet's rotation, form complex spirals and helices that thread through the entire liquid core. Now comes the crucial step in magnetic field generation. Moving iron, like any flowing electrical conductor, carries electrical currents. And according to the laws of physics discovered by scientists like Michael Faraday and James Clerk Maxwell in the 19th century, moving electrical currents always generate magnetic fields. The swirling, spiraling flows of liquid iron in Earth's core act like the wires in a vast planet-sized dynamo, generating electrical currents that produce the magnetic field we observe at Earth's surface. This process, known as the geodynamo, is one of the most complex and fascinating phenomena in the natural world. Unlike the simple bar magnets we might use to pick up paper clips, Earth's magnetic field is generated by the continuous motion of electrically conducting fluid. The magnetic field, once created, actually influences the motion of the iron that created it, setting up a complex feedback loop that has sustained Earth's magnetism for billions of years. The strength and orientation of Earth's magnetic field depend on the details of these fluid motions deep in the core. When the convective flows align in certain patterns, they can strengthen the field. When they become turbulent or change direction, the field may weaken or even reverse entirely. This dynamic relationship between core fluid motion and magnetic field generation means that Earth's magnetism is never truly stable. It fluctuates on timescales ranging from years to millions of years, reflecting the ever-changing patterns of flow in the liquid iron far below our feet. The magnetic field lines generated by the geodynamo extend far beyond Earth's surface, creating what scientists call the magnetosphere. This invisible bubble of magnetic influence stretches tens of thousands of miles into space on the side of Earth facing the Sun, and even farther on the side facing away from our star. The shape of this magnetic envelope is constantly sculpted by the solar wind, a stream of charged particles flowing outward from the Sun at speeds of hundreds of miles per second. When the solar wind encounters Earth's magnetosphere, it cannot penetrate the magnetic barrier. Instead, it flows around our planet like water around a stone in a stream, compressing the magnetic field on the sunward side and stretching it out into a long tail on the opposite side. This interaction creates a complex, dynamic boundary between the solar wind and Earth's magnetic field, a frontier where the forces of our planet and our star meet in an endless cosmic battle. The magnetosphere serves as Earth's first line of defense against the harsh radiation environment of space. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, as it appears to have done to Mars billions of years ago. The charged particles that make up the solar wind would also reach Earth's surface, creating radiation levels that would be lethal to most forms of life as we know it. But the geodynamo that creates this protective field is not a simple, steady process. The flows in Earth's liquid core are turbulent and chaotic, influenced by temperature variations, chemical reactions, and the complex interplay between Earth's rotation and the convective forces driving the motion of teamed, molten iron. This means that Earth's magnetic field is constantly changing, sometimes strengthening, sometimes weakening, and occasionally undergoing dramatic reversals where north becomes south and south becomes north. These magnetic reversals, recorded in rocks around the world, provide us with a window into the deep history of Earth's core and the long-term behavior of the geodynamo. By studying how the magnetic field has changed over geological time, scientists can begin to understand the complex processes operating in Earth's interior and perhaps even predict how our magnetic shield might behave in the future. The story of Earth's magnetic field is ultimately a story about the dynamic nature of our planet. Far from being a static, unchanging rock floating in space, Earth is a complex, active world where the processes operating in the deep interior continue to shape conditions at the surface billions of years after our planet first formed. The liquid iron currents flowing nearly 3,000 miles beneath our feet are as important to life on Earth as the atmosphere we breathe or the water we drink. For without the magnetic field they generate, our world would be a very different and far more hostile place. Mapping the invisible shield, the invisible nature of Earth's magnetic field, presents unique challenges for those who wish to study it. Unlike mountains or rivers, which can be seen and measured directly, the magnetic field can only be detected through its effects on magnetized objects and charged particles. Yet over the centuries, patient observers have developed increasingly sophisticated methods to map this invisible shield, revealing its complex three-dimensional structure and its subtle variations across our planet's surface. The earliest systematic attempts to map Earth's magnetic field began with the observations of mariners during the Age of Exploration. As ships ventured into previously uncharted waters, navigators carefully recorded the behavior of their compass needles, noting how magnetic declination, the difference between magnetic north and true north, varied from place to place. These observations, accumulated over decades of oceanic voyaging, began to reveal the global pattern of Earth's magnetic field. One of the first scientists to recognize the significance of these maritime observations was Edmund Halley, the English astronomer famous for the comet that bears his name. In the late 17th century, Halley compiled compass readings from ships across the Atlantic Ocean and created the first isogonic chart, a map showing lines of equal magnetic declination. These gracefully curved lines revealed that Earth's magnetic field was far more complex than anyone had previously imagined, varying in both strength and direction in patterns that seemed to follow some hidden global logic. Halley's work marked the beginning of systematic magnetic surveying, but the tools available to early investigators were crude by modern standards. Compass readings could be affected by iron objects aboard ships, by local magnetic anomalies in the Earth's crust, and by the constant motion of vessels at sea. More precise instruments were needed to map the magnetic field accurately, and these began to appear during the 18th and 19th centuries. The magnetic dip needle, invented in the 16th century but refined during the Enlightenment, measured the inclination of magnetic field lines their angle relative to Earth's surface. At the magnetic equator, where field lines run parallel to the ground, a magnetic needle balances horizontally. As one moves toward the magnetic poles, the field lines plunge more steeply into the Earth, causing the needle to tip progressively more toward the vertical. By measuring this magnetic inclination at different locations, scientists could map the three-dimensional structure of the magnetic field with unprecedented precision. Perhaps the most ambitious magnetic survey of the 19th century was undertaken by Carl Friedrich Gauss, the German mathematical genius whose contributions to science extended far beyond his famous Beefray work in mathematics. Gauss realized that to truly understand Earth's magnetic field, measurements would need to be made simultaneously at multiple locations around the world, using instruments calibrated to the same standards. In the 1830s and 1840s, he organized an international network of magnetic observatories, creating what may have been the first global scientific collaboration in history. The Göttingen Magnetic Union, as this network came to be known, established observatories from London to Beijing, from St. Petersburg to Cape Town. On designated days, observers at all these locations would make simultaneous measurements of magnetic declination, inclination, and intensity, creating snapshots of Earth's magnetic field at specific moments in time. These coordinated observations revealed that the magnetic field was not constant but fluctuated on timescales ranging from hours to years, suggesting that its source was dynamic rather than static. Gauss made another crucial contribution to magnetic field mapping through his mathematical analysis of the global data. He developed a technique, now known as spherical harmonic analysis, that could separate the magnetic field into components of different origins. Most of Earth's magnetic field, Gauss showed, originated from sources deep within the planet, confirming that the field was generated internally rather than by external causes like the sun or stars. But his analysis also revealed smaller contributions from sources in Earth's crust and from electrical currents flowing high in the atmosphere. The 19th century also saw the beginning of systematic magnetic surveys on land. Teams of scientists, often accompanying military expeditions or geological surveys, carried portable magnetometers across continents, measuring the magnetic field at thousands of locations. These terrestrial surveys revealed that the smooth, global patterns detected by maritime observations were complicated by local magnetic anomalies associated with deposits of iron ore, volcanic rocks, other magnetic materials in Earth's crust. One of the most remarkable land-based magnetic surveys was conducted by James Clark Ross during his Antarctic expeditions in the 1840s. Ross, already famous as an Arctic explorer, led a 3-ship expedition to the southern continent with the specific goal of locating the South Magnetic Pole, the point where Earth's magnetic field lines plunge vertically downward into the planet. After months of careful measurement in the hostile Antarctic environment, Ross successfully located the South Magnetic Pole, confirming that Earth truly behaved like a giant dipole magnet with 2 poles roughly opposite each other. But Ross's measurements also revealed something puzzling about Earth's magnetic poles. Unlike the geographic poles, which are fixed points defined by Earth's rotation, the magnetic poles seemed to move. Subsequent observations confirmed that both the north and south magnetic poles wandered slowly across Earth's surface, their positions shifting by miles each year. This discovery provided the first clear evidence that Earth's magnetic field was generated by dynamic processes in the planet's interior. The advent of more sensitive instruments in the 20th century revolutionized magnetic field mapping. The fluxgate magnetometer, developed during World War II for submarine detection, could measure magnetic field strength with far greater precision than previous instruments. Proton precession magnetometers, invented in the 1950s, provided even higher accuracy by measuring the behavior of hydrogen atoms in Earth's magnetic field. These instruments made it possible to detect tiny variations in magnetic strength that revealed the detailed structure of the field and its changes over time. Airborne magnetic surveys, first conducted in the 1940 ES, allowed scientists to map magnetic fields over large areas quickly and efficiently. Aircraft equipped with sensitive magnetometers could survey entire continents in a matter of months, revealing magnetic anomalies associated with geological structures buried deep beneath Earth's surface. These surveys proved invaluable for mineral exploration and geological mapping, but they also contributed to our understanding of the global magnetic field by providing dense coverage of regions that were difficult to reach on foot. The space age brought an entirely new perspective to magnetic field mapping. Satellites orbiting hundreds of miles above Earth's surface could measure the magnetic field without interference from local crustal anomalies, providing the clearest view yet of the field generated by the core. The first magnetic satellite, OGO-2, launched in 1965, confirmed the dipolar nature of Earth's main magnetic field, while revealing complex smaller-scale features that varied with park, location, and time. More recent satellite missions have provided increasingly detailed maps of Earth's magnetic field. The Danish Ørsted satellite, launched in 1999, measured the field with unprecedented precision for nearly 2 decades. The German Chant satellite, operational from 2000 to 2010, provided continuous monitoring of magnetic field changes. The European Space Agency's Swarm constellation, consisting of 3 satellites launched in 2013, continues to map Earth's magnetic field in extraordinary detail, revealing its structure and evolution with clarity that would have been unimaginable to early magnetic pioneers like Halley and Gauss. These modern satellite observations have revealed that Earth's magnetic field is far more complex than the simple dipole model suggested by early investigators. While the dipole component dominates, contributing about 90% of the field at Earth's surface, there are also quadrupole, octupole, and higher-order components that create regional variations in field strength and direction. The field is strongest near the magnetic poles, where it reaches intensities of about 65, 000 nanotesla, and weakest near the magnetic equator, where it drops to about 25, 000 nanotesla. The detailed maps produced by satellite observations have also revealed that Earth's magnetic field is weakening. Over the past 150 years, the dipole momenta measure of the field's overall strength has decreased by about 10%. This decline is not uniform across the globe. Some regions have experienced much larger decreases, while others have actually seen slight increases. The South Atlantic anomaly, a region where the magnetic field is particularly weak, has been expanding and deepening, creating concerns about increased radiation exposure for satellites and astronauts passing duty through this area. Perhaps most intriguingly, satellite observations have shown that the magnetic field is changing rapidly on human timescales. The positions of the magnetic poles continue to drift, with the North Magnetic Pole currently moving towards Siberia at a rate of about 35 miles per year. The field's strength and direction fluctuate from year to year, reflecting changes in the fluid motions deep within Earth's core. These rapid changes suggest that Earth's magnetic field is far more dynamic than previously thought, capable of significant variations over decades or centuries rather than only over geological timescales. The ability to map Earth's magnetic field in such detail has profound implications for our understanding of our planet's interior. By studying how the field changes over time, scientists can infer the patterns of fluid motion in the liquid iron core, gaining insights into processes occurring nearly 3,000 miles beneath our feet. These observations are also crucial for understanding how Earth's magnetic field might behave in the future, particularly whether it might weaken significantly or undergo a complete reversal in the coming centuries. The invisible shield that surrounds our planet has thus become increasingly visible through human ingenuity and persistence. From the simple compass observations of medieval navigators to the sophisticated satellite measurements of today, each generation of magnetic field mappers has revealed new aspects of this fundamental feature of our world, gradually building our understanding of the dynamic processes that protect life on Earth from the harsh environment of space. Magnetic reversals. When north becomes south, among the most fascinating and mysterious aspects of Earth's magnetic field is its tendency to reverse itself, switching the positions of magnetic north and south in what appears to be an irregular, unpredictable pattern. These magnetic reversals represent one of the most dramatic changes our planet can undergo, transforming the very orientation of the invisible shield that protects us from cosmic radiation. Yet for most of human history, the occurrence of these reversals remained completely unknown, hidden in the geological record like chapters in an ancient book written in stone. The first hints that Earth's magnetic field might have been different in the past emerged in the early 20th century, when scientists studying volcanic rocks made a puzzling discovery. When certain types of igneous rock cool from their molten state, iron-bearing minerals within them become magnetized in the direction of the ambient magnetic field, essentially freezing a record of the field's orientation at the time the rock solidified. Most volcanic rocks showed magnetization aligned with the current magnetic field, as expected, but some displayed magnetization pointing in exactly the opposite direction, as if they had formed when magnetic north and south were reversed. Initially, many scientists dismissed these observations as experimental errors or the result of rocks being physically overturned after they had formed. The idea that Earth's magnetic field could completely reverse itself seemed too extraordinary to accept readily. After all, the magnetic field appeared remarkably stable on human timescales, maintaining essentially the same orientation throughout recorded history. How could such an apparently permanent feature of our planet undergo such dramatic changes? The breakthrough came through the systematic study of sequences of volcanic rocks, particularly the basaltic lavas that form when volcanic eruptions create layer upon layer of solidified rock. In places like Iceland, the western United States, and other volcanically active regions, these rock sequences preserve records of magnetic field orientation extending back millions of years. By carefully measuring the magnetic orientation of rocks at different levels in these sequences, scientists could reconstruct the history of Earth's magnetic field with unprecedented detail. The patterns that emerged from these studies were remarkable. Rather than showing random fluctuations, the magnetic orientations alternated between two distinct states: periods when the magnetic field pointed roughly toward the current magnetic north, called normal polarity, and periods when it pointed toward the current magnetic south, called reversed polarity. Each polarity interval lasted anywhere from thousands to millions of years, separated by relatively brief periods of transition when the field appeared to fluctuate wildly before settling into the opposite papyri. Orientation. These discoveries revolutionized our understanding of Earth's magnetic field and led to the development of an entirely new scientific discipline called paleomagnetism, the study of ancient magnetic fields recorded in rocks. Paleomagnetic studies revealed that magnetic reversals had been occurring throughout Earth's history, creating a complex pattern of alternating polarity intervals that extended back hundreds of millions of years into the geological past. But the most dramatic confirmation of magnetic reversals came from an unexpected source: the ocean floor. In the 1950s and 1960s, as scientists began systematically mapping the sea bottom using newly developed sonar technology, they discovered that the oceanic crust displayed remarkable magnetic patterns. Parallel stripes of alternating magnetic polarity extended across entire ocean basins, creating what looked like vast magnetic barcodes printed on the sea floor. The explanation for these oceanic magnetic patterns provided crucial evidence for the theory of plate tectonics and seafloor spreading. As molten rock erupts at mid-ocean ridges, it solidifies in the ambient magnetic field, recording the field's orientation at that time. As the oceanic plates slowly move away from these underwater mountain ranges, they carry with them this magnetic signature, creating a symmetrical pattern of magnetic stripes on both sides of each ridge. When Earth's magnetic field reverses, newly formed oceanic crust records the reversed orientation, creating the next stripe in the pattern. These oceanic magnetic patterns allowed scientists to construct detailed timescales of magnetic reversals extending back more than 160 million years. The resulting magnetic polarity timescale reveals a complex history of field reversals, with some eras characterized by frequent reversals occurring every few 100,000 years, while others, known as supercrons, show stable polarity for tens of millions of years. The current normal polarity interval, known as the Bruns chrom, began about 780,000 years ago and represents the longest period of magnetic stability in the past 5 million years. The mechanism underlying magnetic reversals remains one of the most challenging problems in Earth sciences. The reversals clearly originate from changes in the fluid motions within Earth's liquid iron core, but the specific processes that trigger these dramatic reorientations of the magnetic field are not fully understood. Computer simulations of the geodynamo suggest that reversals occur when the complex turbulent flows in the core undergo certain types of reorganization, but predicting when these changes might occur has proved essentially impossible. What is clear from both observations and theoretical studies is that magnetic reversals are not instantaneous events. The process of reversal appears to unfold over several thousand years, during which the magnetic field weakens significantly and may develop multiple poles instead of the usual dipuair configuration. During these transition periods, the magnetic field provides reduced protection from cosmic radiation, potentially affecting Earth's atmosphere and climate in ways that are still being investigated. The transition process typically begins with a gradual weakening of the dipolar field, followed by the growth of more complex field configurations with multiple magnetic poles scattered around the globe. The field may fluctuate between different orientations several times before finally settling into the opposite polarity. During the most chaotic phases of reversal, the magnetic field strength may drop to as little as 10% of its normal value, leaving Earth's atmosphere more exposed to the solar wind and cosmic radiation. Studies of sediment cores from the ocean floor and ancient lakes have provided detailed records of several magnetic reversals, including the most recent major reversal, 780,000 years ago. These records show that the reversal process is complex and varies from one event to another. Some reversals appear to proceed relatively smoothly from one polarity to the other, while others involve multiple failed attempts at reversal, with the field weakening and beginning to reverse before recovering its original power. Orientation. The frequency of magnetic reversals has varied dramatically throughout the Earth's history. During the past 5 million years, reversals have occurred on average about every 200,000 to 300,000 years, but this rate has not been constant. Some periods have seen reversals as frequently as every 50,000 years, while others have experienced millions of years without any reversals at all. The longest known period of stable polarity, the Cretaceous normal superchrom, lasted about 35 million years and ended roughly 85 million years ago. The causes of this variability in reversal frequency remain mysterious. Some scientists have proposed that changes in heat flow from the core to the mantle might influence reversal rates, while others have suggested that the reversal frequency might be related to variations in Earth's rotation or to periodic changes in the core's composition. The correlation between reversal frequency and other geological processes, such as mountain building or mass extinction events, has also been investigated, but no clear causal relationships have been established. One of the most intriguing aspects of magnetic reversals is their potential impact on life. While the geological record does not show any clear correlation between reversals and mass extinction events, the weakened magnetic field during reversal transitions would allow increased cosmic radiation to reach Earth's surface. This increased radiation could potentially affect the ozone layer, alter atmospheric chemistry, and influence global climate patterns. Some researchers have suggested that magnetic reversals might have played a role in human evolution, as several reversal events coincided with significant changes in early human populations, though such correlations remain speculative. The study of magnetic reversals has also provided crucial insights into the deep structure and dynamics of Earth's core. The fact that reversals occur at all demonstrates that the geodynamo is a complex, nonlinear system capable of dramatic reorganization. The patterns of reversal timing and the detailed structure of reversal transitions provide constraints on theoretical models of core dynamics, helping scientists understand the fundamental processes that generate and maintain Earth's magnetic field. Modern satellite observations have revealed that Earth's current magnetic field is undergoing changes that some scientists interpret as possible precursors to a future reversal. The overall strength of the dipole field has been decreasing for the past 150 years, and the South Atlantic anomaly, a region of particularly weak magnetic field over the South Atlantic Ocean, has been growing and intensifying. The North Magnetic Pole has also been accelerating its movement toward Siberia, behavior that some models suggest could indicate an approaching reversal. However, predicting whether or when a reversal might occur remains extremely difficult. The magnetic field has weakened and shown unusual behavior many times in the past without undergoing a complete reversal. Some of these events, called excursions, involve temporary departures from normal dipolar field geometry followed by recovery of the original polarity. The most recent major excursion, the Lachamp event, occurred about 41,000 years ago and lasted for several centuries before the field returned to its normal configuration. The geological record of magnetic reversals continues to be one of our most important sources of information about Earth's deep interior and its long-term evolution. Each reversal preserved in volcanic rocks or ocean floor basalts provides a snapshot of the magnetic field at a specific time in Earth's history, allowing scientists to trace the evolution of the geodynamo over millions of years. These records also serve as crucial calibration points for theoretical models of core dynamics, helping researchers understand the complex feedback mechanisms that control the generation and maintenance of planetary magnetic fields. As we continue to monitor Earth's current magnetic field using satellites and ground-based observatories, we are witnessing in real time the ongoing evolution of the same dynamic system that has undergone hundreds of reversals throughout our planet's history. Whether we are approaching another reversal or simply observing the normal fluctuations of a complex system remains to be seen. But our growing understanding of magnetic reversals provides valuable insights into one of the most fundamental and mysterious aspects of our dynamic planet. The aurora, Earth's magnetic light show away, where our Sun converts 4 million tons of matter into energy every second through the process of nuclear fusion. This tremendous energy release sends streams of charged particles racing outward through space at velocities approaching 1,000,000 miles per hour. This solar wind, composed primarily of protons and electrons stripped from hydrogen atoms in the Sun's corona, flows continuously past all the planets in our solar system, carrying with it a portion of the Sun's Samonchen magnetic field. When this solar wind encounters Earth's magnetosphere, it cannot simply pass through our planet's magnetic field as it would through empty space. Instead, the charged particles in the solar wind interact with Earth's magnetic field lines in complex ways, guided by the fundamental principle that charged particles must follow the invisible highways laid out by magnetic forces. Most of these particles are deflected around Earth, flowing past our planet like water around a stone. But some become trapped in Earth's magnetic field, creating regions of accumulated charged particles, called the Van Allen radiation belts. Under normal conditions, Earth's magnetic field successfully channels most of the solar wind around our planet, maintaining the boundary between our magnetosphere and the hostile space environment. But the Sun is not a constant, steady star. Solar activity varies on cycles ranging from minutes to years, and during periods of increased activity, the solar wind can become a raging torrent of charged particles capable of overwhelming Earth's magnetic defenses. Solar storms triggered by magnetic reconnection events on the Sun's surface can release massive clouds of plasma called coronal mass ejections. When these clouds of charged particles reach Earth, they can compress our magnetosphere violently, forcing some of the solar wind particles deep into regions normally protected by our magnetic field. These disturbed conditions set the stage for aurora formation, as the compressed magnetosphere allows charged particles to penetrate much closer to Earth than they normally could. The key to understanding auroral light lies in recognizing that charged particles entering Earth's atmosphere must follow the planet's magnetic field lines, which guide them toward the magnetic poles like invisible funnels. As these particles spiral along the magnetic field lines, they gradually lose altitude, eventually entering the upper atmosphere at heights between 60 and 600 miles above Earth's surface. Here, in the thin air of the thermosphere and mesosphere, they begin to collide with atmospheric gases. The most common auroral color, a pale yellowish green, occurs when high-energy electrons strike oxygen atoms at altitudes around 60 to 100 miles above the surface. These collisions excite the oxygen atoms, adding energy to their electrons and pushing them into higher energy states. When the excited electrons fall back to their normal energy levels, they release the excess energy as light with a wavelength of 557, 7 nanometers, creating the characteristic green glow that dominates most auroral displays. At higher altitudes, typically above 150 miles, oxygen atoms produce a different color when excited by incoming particles. Here, the thinner atmosphere allows excited oxygen atoms more time to emit light before being disturbed by collisions with other atoms. Under these conditions, oxygen produces a deeper red emission at 630.0 nanometers, creating the crimson curtains that often crown auroral displays. This red light is much fainter than the green emission, requiring darker skies and more sensitive eyes to observe clearly. Nitrogen, the most abundant gas in Earth's atmosphere, also contributes to auroral colors, though less commonly than oxygen. When struck by particularly energetic particles, nitrogen molecules can produce blue or purple light, adding these rarer hues to the auroral palette. The exact colors visible during any particular auroral display depend on the energy of the incoming particles, the altitude at which collisions occur, and the composition of the atmosphere at those heights. The characteristic curtain-like structure of aurora results from the three-dimensional geometry of Earth's magnetic field lines. These invisible lines of force curve from the magnetic equator toward the magnetic poles, creating a complex pattern that guides charged particles along specific paths through the upper atmosphere. When particles follow neighboring field lines, they create parallel columns of light that appear from the ground as luminous curtains hanging in the sky. The movement and dancing motion of aurora reflect the constantly changing conditions in the magnetosphere and solar wind. As the pressure and direction of the solar wind vary, Earth's magnetic field lines shift and reorganize themselves, causing the paths followed by charged particles to change correspondingly. This creates the characteristic flowing, rippling motion of auroral curtains, as if they were enormous flags waving in a cosmic wind. The oval-shaped regions around Earth's magnetic poles where aurora most commonly appear are called the auroral ovals. These regions, typically located between 60 and 70 degrees magnetic latitude, mark the areas where Earth's magnetic field lines provide the most direct paths for solar wind particles to enter the beaten atmosphere. The size and position of the auroral ovals change with solar activity during quiet periods. They contract toward the poles, while during magnetic storms, they expand toward the equator, sometimes bringing aurora to latitudes where they are rarely seen. Throughout human history, aurora have inspired wonder, fear, and countless myths and legends. Indigenous peoples of the Arctic regions developed rich traditions around these lights, often interpreting them as the spirits of ancestors dancing in the sky or as pathways used by souls traveling to the afterlife. The Inuit of Alaska believed that aurora were the spirits of animals they had hunted, while some Scandinavian cultures saw them as reflections of light from the shields and armor of the Valkyries as they rode across the heavens. The scientific study of aurora began in earnest during the 18th century, when systematic observations revealed their connection to Earth's magnetic field. The Norwegian scientist Christian Birkeland conducted pioneering research in the early 20th century, using laboratory experiments with magnetized spheres and electron beams to demonstrate how charged particles from space could create auroral-like phenomena. His work laid the foundation for our modern understanding of aurora as the visible manifestation of the interaction between the solar wind and Earth's magnetosphere. Modern research has revealed that aurora are far more complex than early investigators imagined. High-resolution observations from ground-based cameras and spacecraft have shown that auroral light often contains fine-scale structures called auroral arcs, which can be as narrow as a few hundred meters across. These arcs often display rapid flickering and pulsating behavior, reflecting small-scale turbulence and instabilities in the plasma flowing along magnetic field lines. Perhaps most remarkably, Aurora are not unique to Earth. Every planet in our solar system with a significant magnetic field produces its own auroral displays. Jupiter, with its powerful magnetic field and 4 large moons that supply charged particles, hosts aurora far more intense than any seen on Earth. Saturn's aurora, often observed in ultraviolet light by space-based telescopes, reveal the complex interaction between the solar wind and the planet's magnificent ring system. Even Mars, which lacks a global magnetic field, produces localized aurora over regions where ancient magnetic fields are preserved in its crust. The study of aurora continues to provide crucial insights into the fundamental physics of plasma and magnetic fields, both in our immediate space environment and throughout the universe. The same processes that create Earth's aurora also operate in the magnetospheres of other planets, in the solar corona, and in the vicinity of distant stars and galaxies. By understanding how charged particles interact with magnetic fields in the relatively accessible environment around Earth, scientists gain tools for interpreting similar phenomena occurring throughout the cosmos. For those fortunate enough to witness a major auroral display, the experience often proves unforgettable. Standing beneath curtains of light that stretch from horizon to horizon, watching them dance and pulse with colors that seem to emanate from another world, one cannot help but feel connected to the vast electromagnetic forces that shape our planet and our solar system. In these moments, the invisible magnetic field that surrounds us becomes visible, revealing itself as a dynamic, living entity that connects Earth to the star that gives us life. The aurora remind us that our planet does not exist in isolation, but is intimately connected to the broader cosmos. The same stellar winds that created the first auroral displays billions of years ago continue to interact with Earth's magnetic field today, creating a light show that has remained essentially unchanged since the first humans looked up at the night sky in wonder. In this sense, the aurora represent one of our most direct connections to the universe beyond our world, a visible reminder of the invisible forces that shape our planet's destiny. As we face an uncertain future for Earth's magnetic field, with its current weakening trend and the possibility of future reversals, the aurora may themselves undergo changes. A significantly weakened magnetic field would allow charged particles to penetrate deeper into our atmosphere, potentially altering the altitude, intensity, and geographic distribution of auroral displays. While such changes would likely unfold over many human generations, they serve as a reminder that even phenomena as seemingly eternal as the aurora are ultimately subject to the dynamic evolution of our planet's magnetic environment. The next time you see a photograph of the aurora borealis or aurora australis, remember that you are looking at visible evidence of Earth's magnetic field in action. Those shimmering curtains of light represent the intersection of the terrestrial and the cosmic, where particles from our Sun follow invisible magnetic highways to create one of nature's most spectacular displays. In the dance of the aurora, we can glimpse the complex electromagnetic forces that have protected life on Earth for billions of years and continue to shape our world's interaction with the cosmos today. Future research into auroral phenomena promises to deepen our understanding of Earth's magnetic field and its evolution over time. New ground-based instruments and space missions are providing unprecedented detail about the small-scale processes that create auroral light, while long-term monitoring programs are revealing how aurora respond to changes in Earth's magnetic field and solar activity. As we continue to study these magnificent displays, we gain not only scientific knowledge but also a deeper appreciation for the invisible forces that make life on our planet possible. The auroras stand as testament to the dynamic nature of our planet and its place in the solar system. They remind us that Earth is not a static rock floating in space, but an active world whose magnetic field reaches far beyond our atmosphere, creating an invisible bridge between our terrestrial home and the vast electromagnetic environment of interplanetary space. In their ethereal beauty, we find both scientific wonder and spiritual inspiration, a perfect expression of the profound connections that link our planet to the cosmos that surrounds us. When early humans first witnessed these mysterious lights dancing across the polar skies, they had no way of knowing that they were observing direct evidence of the magnetic field that protects all life on Earth. Today, we understand that every photon of auroral light represents a small victory of our planet's magnetic shield, a charged particle from space that was guided safely away from our atmosphere to create beauty instead of destruction. In this way, the aurora serve as a nightly reminder of the invisible guardian that has watched over our world since the earliest days of our planet's history. Moving forward through our exploration of Earth's magnetic field, we encounter a more troubling question. What would happen if this protective shield were to fail? The magnetic field that creates the aurora and deflects the solar wind is not a permanent feature of our planet. It has weakened before, reversed itself countless times, and could potentially disappear entirely under the right circumstances. Understanding these possibilities and their potential consequences for life on Earth brings us to consider the darker side of our planet's magnetic history and the uncertain future that may lie ahead. The prospect of a world without its magnetic shield forces us to confront the fundamental vulnerability of life on our planet. While the magnetic field has protected us for billions of years, it is ultimately a product of dynamic processes in Earth's core that could change or cease under conditions we do not fully understand. The same molten iron currents that create our protective magnetosphere today could reorganize themselves tomorrow in ways that might leave our planet as magnetically naked as Mars. To understand what such a future might hold, we must examine worlds where magnetic fields have already failed and consider the mechanisms by which planetary magnetism can be lost. Mars provides perhaps the most sobering example of a world that once possessed a strong magnetic field, but lost it early in its history. The red planet's surface bears scars from this magnetic catastrophe, written in its thin atmosphere and radiation-scoured landscape. By studying Mars and other magnetically inactive worlds, we can begin to appreciate the true importance of Earth's magnetic field and the potential consequences of its loss. The geological evidence from Mars suggests that our planetary neighbor once possessed a magnetic field comparable in strength to Earth's current field. Magnetized minerals in ancient Martian rocks record the presence of this field during the planet's first few 100 million years, a period when Mars may have been warm enough to support liquid water on its surface. However, sometime around 4 billion years ago, Mars's magnetic field began to weaken dramatically, and within a few 100 million years, it had essentially disappeared. The loss of Mars's magnetic field appears to be linked to the cooling and solidification of the planet's core. Mars, being smaller than Earth, cooled more rapidly after its formation, causing the convective currents in its molten iron core to slow and eventually cease. Without these fluid motions to drive the dynamo process, Mars's magnetic field faded away, leaving the planet defenseless against the solar wind. The consequences of this magnetic failure for Mars were profound and irreversible. Without a magnetic field to deflect the solar wind, charged particles from the Sun began stripping away Mars's atmosphere directly. Over millions of years, this atmospheric erosion reduced the dense, potentially life-supporting atmosphere that Mars may once have possessed to the thin, cold envelope of gas we observe today. The process continues even now, with spacecraft observations showing that Mars loses about 2 pounds of atmospheric gas to space every second. Earth faces no immediate risk of suffering the same fate as Mars, primarily because our planet's larger size means that its core will remain molten and convective for billions of years to come. The heat generated by radioactive decay in Earth's interior, combined with the enormous thermal mass of our planet, ensures that the geodynamo will continue operating for the foreseeable geological future. However, this does not mean that Earth's magnetic field is immune to dramatic changes or temporary failures. The paleomagnetic record shows that Earth's magnetic field has undergone numerous complete reversals throughout its history, during which the field weakened significantly before reorganizing itself with opposite polarity. During the transition periods associated with these reversals, which can last several thousand years, Earth's magnetic field may drop to as little as 10% of its normal strength. Some scientists have speculated that during these intervals of magnetic weakness, our planet may experience increased atmospheric loss, similar to what occurred on Mars, though on a much smaller scale. Modern satellite observations have revealed that Earth's magnetic field is currently in a state of significant change. The overall strength of the dipole field has been decreasing steadily for the past 150 years, leading some researchers to speculate that we may be approaching another magnetic reversal. The South Atlantic anomaly, a region over the South Atlantic Ocean where the magnetic field is particularly weak, has been growing and intensifying, allowing increased radiation to reach the upper atmosphere in this area If Earth's magnetic field were to weaken substantially or disappear entirely, even temporarily, the consequences for our modern technological civilization could be severe. The increased radiation reaching our atmosphere would pose significant risks to satellites, spacecraft, and astronauts, while the disruption of the magnetosphere could interfere with radio communications and detain navigation systems worldwide. Airlines would need to reroute flights to avoid high-radiation polar regions, and power grids could face increased vulnerability to solar storms. More fundamentally, a severely weakened magnetic field could begin to affect Earth's atmosphere and climate. While our planet's much stronger gravity compared to Mars would prevent rapid atmospheric loss, increased solar radiation reaching the upper atmosphere could alter the chemistry of the ozone layer and affect global weather patterns. Some scientists have suggested that past periods of weak magnetic field may have contributed to ice ages or other climate changes, though such connections remain speculative and controversial. The biological effects of increased cosmic radiation during periods of magnetic field weakness are also a subject of ongoing research. While Earth's atmosphere provides substantial protection against space radiation even when the magnetic field is weak, the increased radiation levels could potentially affect the evolution of life on our planet. Some researchers have suggested that magnetic reversals might be linked to extinction events or evolutionary changes, though definitive evidence for such connections has proved elusive. Perhaps more relevant to modern concerns is the question of how human technology would fare during a magnetic field reversal or significant weakening. Our increasingly interconnected, satellite-dependent civilization relies heavily on technologies that are vulnerable to space radiation and magnetic disturbances. A prolonged period of weak magnetic field could disrupt communications, navigation, and power systems in ways that our ancestors, who lived through previous reversals without technological assistance, never had to face. The study of Earth's magnetic field and its potential future changes has thus become not just a matter of scientific curiosity, but a question of practical importance for human civilization. Understanding how the magnetic field might evolve over the coming centuries and millennia could be crucial for preparing our technology and infrastructure to withstand periods of magnetic instability. This has led to increased investment in magnetic field monitoring and research, as scientists work to develop better models of the geodynamo and improve our ability to predict magnetic field changes. Current research efforts include sophisticated computer simulations of the geodynamo process, designed to understand the complex fluid dynamics and electromagnetic interactions that generate Earth's magnetic field. These models, run on some of the world's most powerful supercomputers, are beginning to reproduce some aspects of magnetic field behavior, including reversals and variations in field strength. However, the chaotic nature of the fluid motions in Earth's core makes long-term prediction extremely challenging, similar to the difficulties faced in weather forecasting, but extended over much longer timescales. International cooperation in magnetic field research has also intensified, with space agencies around the world launching satellites designed to monitor Earth's magnetic field in unprecedented detail. The European Space Agency's SWARM mission, consisting of 3 satellites orbiting at different altitudes, provides continuous monitoring of magnetic field changes and has already revealed new aspects of how the field is generated and how it evolves over time. These observations are crucial for understanding whether the current weakening trend represents the beginning of a reversal or simply a normal fluctuation in field strength. Ground-based magnetic observatories around the world also continue to play a vital role in monitoring Earth's magnetic field. These stations, some of which have been operating for more than a century, provide long-term records of magnetic field changes that are essential for understanding the natural variability of the field and for DACI, calibrating satellite observations. The global network of magnetic observatories represents one of the longest-running international scientific collaborations, demonstrating the worldwide importance of understanding our planet's magnetic press. Environment. As we look toward the future, the question of Earth's magnetic field evolution remains one of the most important and challenging problems in Earth sciences. While we cannot predict exactly when the next magnetic reversal might occur, or how severe the next period of magnetic weakness might be, we can continue to study and monitor our planet's magnetic field to better understand its behavior and prepare for potential changes. The story of Earth's magnetic field is ultimately a story about the dynamic nature of our planet and the delicate balance of forces that make life possible. From the ancient discovery of magnetic stones to the modern satellite monitoring of the magnetosphere, human understanding of this invisible shield has grown dramatically, yet many fundamental questions remain unanswered. The magnetic field that protects us today is the product of processes operating deep within our planet, processes that have continued for billions of years but which remain among the most complex and challenging phenomena in all of natural science. In contemplating the hidden history of Earth's magnetic field, we gain not only scientific knowledge, but also a deeper appreciation for the remarkable circumstances that have allowed life to flourish on our planet. The invisible shield that surrounds us represents one of the key differences between Earth and the other rocky planets in our solar system, a difference that may have made all the difference for the emergence and evolution of life as DTS. We know it. The magnetic field connects us to the deepest parts of our planet and to the farthest reaches of space, linking the churning iron currents nearly 3,000 miles beneath our feet to the solar wind streaming from our star. In this connection, we find a profound reminder of our place in the universe not as isolated beings on a static rock, but as participants in a vast, interconnected system of electromagnetic forces that spans from the center of the Earth to the edge of the solar system and beyond. As we continue to study and monitor Earth's magnetic field, we are not just satisfying scientific curiosity, but also working to understand and protect one of the fundamental conditions that makes our world habitable. The hidden history of Earth's magnetic field is still being written, chapter by chapter, in the ongoing dance between the molten iron in our planet's core and the charged particles streaming from the Sun. Our role, as both observers and participants in this cosmic drama, is to continue learning, continue monitoring, and continue marveling at the invisible forces that have shaped our world and will continue to shape it for billions of years to come. In the end, perhaps the most remarkable aspect of Earth's magnetic field is not its complexity or its power, but its persistence. For 4.5 billion years, through countless changes in our planet's surface and atmosphere, through the rise and fall of countless species, through the emergence of consciousness and civilization, the magnetic field has continued its silent vigil. It has weakened and strengthened, reversed and recovered, but it has never abandoned its post as guardian of our world. This persistence gives us hope that Earth's magnetic shield will continue to protect us far into the future, even as we work to understand its mysteries and prepare for its inevitable changes. The hidden history of Earth's magnetic field is a story of resilience and adaptation, of invisible forces that have shaped the visible world in ways we are only beginning to understand. It is a story that connects the ancient past to the uncertain future, reminding us that we are part of something much larger and more enduring than our brief individual existence. As we conclude this journey through the hidden history of Earth's magnetic field, we are left with a profound appreciation for the invisible forces that surround us and protect us every moment of our lives. The next time you use a compass to find your way, or look up at the aurora dancing in the polar sky, or simply stand under the stars on a clear night, remember the vast magnetic cocoon that enfolds our planet, the ancient dynamo that generates it, and the cosmic history written in stone that tells its story. The magnetic field that has guided explorers across unknown seas, painted light across the Arctic sky, and protected life itself for billions of years, continues its ancient work today. In its invisible embrace we find both security and wonder, both scientific understanding and poetic mystery. The hidden history of Earth's magnetic field is ultimately our own history, the story of the forces that made our existence possible and continue to shape our destiny among the stars. Yet as we delve deeper into the mysteries of Earth's magnetic field, we discover that our planet's magnetic story extends far beyond the boundaries of our world. The same fundamental processes that generate Earth's protective shield operate throughout the universe, from the smallest planetary bodies to the largest galactic structures. Understanding Earth's magnetism provides us with a key to unlocking the magnetic mysteries of the cosmos itself, revealing connections that span from the depths of our planet to the farthest reaches of space. Throughout our solar system, magnetic fields play crucial roles in shaping planetary environments and determining the potential for life to emerge and survive. Each world tells its own magnetic story, from the robust magnetospheres of the gas giants to the ancient fossilized magnetic signatures preserved in meteorites from the earliest days of our solar system. By comparing Earth's magnetic field to those of other worlds, we gained perspective on both the uniqueness of our own planet and the universal nature of magnetic phenomena. Jupiter, the giant of our solar system, possesses a magnetic field nearly 20,000 times stronger than Earth's. This immense magnetosphere, generated by the rapid rotation of the planet's metallic hydrogen interior, creates radiation belts so intense that they would be lethal to any spacecraft not specifically shielded against them. Jupiter's magnetic field extends so far into space that it would appear larger than the full moon if it were visible to our eyes from Earth. The interaction between this powerful magnetosphere and Jupiter's 4 largest moons creates complex electromagnetic phenomena, including electrical currents flowing between the planet and its satellites that generate more power than all of Earth's electric plants combined. Saturn's magnetic field, while weaker than Jupiter's, displays its own unique characteristics that have puzzled scientists since the Voyager missions first studied it in detail. Unlike most planetary magnetic fields, which are tilted relative to the planet's rotation axis, Saturn's magnetic field appears to be perfectly aligned with its rotational axis, a configuration that theoretical models suggest should be unstable. This perfect alignment may be related to the complex interactions between Saturn's magnetic field and its magnificent ring system, which contains countless charged particles that can influence the planet's magnetosphere in ways we are only beginning to understand. Even more intriguing are the magnetic fields of the ice giants, Uranus and Neptune, which challenge our understanding of how planetary magnetism works. Both of these distant worlds possess magnetic fields that are drastically tilted relative to their rotation axes and offset from their centers, suggesting that their magnetic fields may be generated in their icy mantles rather than in metallic cores like those of the inner planets and gas giants. These unusual magnetic configurations may result from the unique internal structures of these worlds, where layers of water, methane, and ammonia ice create electrical conductivity under the extreme pressures found in planetary interiors. The smaller rocky planets in our solar system tell stories of magnetic loss and preservation that illuminate the fragility and resilience of planetary magnetism. Venus, similar in size to Earth but lacking a magnetic field, demonstrates how a planet can lose its magnetic protection through processes we don't fully understand. Some scientists speculate that Venus may have possessed a magnetic field early in its history, but lost it due to the planet's extremely slow rotation or to catastrophic resurfacing events that disrupted the dynamo process in its core. Mercury presents perhaps the most surprising magnetic story among the rocky planets. Despite its small size and slow rotation, Mercury maintains a weak but detectable magnetic field, suggesting that its iron core remains at least partially molten billions of years after the planet's formation. This persistence of magnetism in such a small world challenges our understanding of planetary cooling and core dynamics, indicating that the processes governing planetary magnetism are more complex, varied than Ernie theories suggested. The moons of the outer planets have revealed their own magnetic secrets, some possessing magnetic fields despite their small sizes, others showing evidence of past magnetic activity preserved in their rocky crusts. Ganymede, Jupiter's largest moon, generates its own magnetic field through a dynamo process operating in its subsurface ocean of liquid water, making it the only moon in our solar system known to possess active magnetosphere. This discovery has profound implications for the possibility of life in the hidden oceans of icy moons, as magnetic fields could provide crucial protection for any organisms that might exist in these alien seas. Europa, another of Jupiter's moons, may also generate magnetic fields through the motion of its subsurface ocean, though the evidence for this is more indirect. When Europa passes through Jupiter's powerful magnetic field, the induced electrical currents in its salty ocean create secondary magnetic fields that spacecraft can detect. This electromagnetic signature provides some of our best evidence for the existence of Europa's hidden ocean, and suggests that the same electromagnetic processes that occur in Earth's core may also operate in the LB, liquid layers of distant moons. The asteroid belt between Mars and Jupiter preserves some of the oldest magnetic records in our solar system. Many meteorites that fall to Earth originated as fragments of asteroids, and some of these rocky visitors carry magnetic signatures that date back to the very formation of our solar system. The magnetic minerals in these ancient rocks record the presence of magnetic fields in the early solar nebula, providing clues about the conditions that existed when the planets were first forming from dust and gas around our crown. The young Sun. These meteoritic magnetic records suggest that magnetic fields played important roles in the formation of planets themselves. The magnetic field present in the early solar nebula may have influenced how dust grains clumped together to form the building blocks of planets, and the magnetic properties of the materials that accreted to form Earth may have affected the development of our planet's own magnetic field. In this sense, Earth's current magnetism may carry within it traces of the cosmic magnetic environment that existed when our solar system was born. Beyond our solar system, astronomers have discovered that magnetic fields are ubiquitous throughout the universe, operating on scales that dwarf even the largest planetary magnetospheres. The Sun itself possesses a complex magnetic field that undergoes an 11-year cycle of strengthening and weakening, creating the sunspot cycles that have been observed and recorded for centuries. During periods of maximum solar magnetic activity, the Sun releases powerful magnetic storms that can affect Earth's magnetosphere and create intense auroral displays visible at latitudes far from the polar regions. The solar magnetic field extends throughout the entire solar system in the form of the interplanetary magnetic field, carried outward by the solar wind and creating a vast magnetic bubble called the heliosphere. The Tingerie encompasses all the planets. This solar magnetic envelope provides the first line of defense against cosmic rays from interstellar space, moderating the radiation environment throughout our solar system. The strength and configuration of the solar magnetic field thus influences the space weather environment that all planets experience, affecting everything from auroral activity on Earth to the radiation levels encountered by spacecraft exploring the outer planets. Recent discoveries have revealed that many other stars also possess magnetic fields, some far more powerful than our Sun's. These stellar magnetic fields can be detected through their effects on starlight, creating subtle changes in the polarization and intensity of light that reaches Earth from distant suns. Young, rapidly rotating stars often display magnetic fields hundreds of times stronger than the Sun's, while older stars tend to have weaker fields as their rotation slows and their magnetic dynamos become less active. The magnetic fields of other stars play crucial roles in determining the habitability of any planets that might orbit them. Strong stellar magnetic fields can create intense stellar winds that strip away planetary atmospheres, while weak magnetic fields may provide insufficient protection against cosmic radiation. The delicate balance required for a star's magnetic field to be compatible with life on orbiting planets adds another layer of complexity to our understanding of what makes a planetary system suitable for the Canti. Emergence and evolution of life. Some of the most extreme magnetic fields in the universe are found around exotic stellar objects like neutron stars and black holes. Neutron stars, the collapsed cores of massive stars that have exploded as supernovas, can possess magnetic fields trillions of times stronger than Earth's. These incredibly powerful magnetic fields accelerate charged particles to nearly the speed of light, creating beams of radiation that sweep across space like cosmic lighthouses. When these beams point toward Earth, we detect them as pulsars, rapidly repeating radio signals that serve as some of the most precise clocks in the universe. Magnetars, a special class of neutron stars with magnetic fields even more powerful than typical pulsars, represent the strongest magnetic fields known to exist anywhere in the universe. The magnetic fields around these objects are so intense that they would be lethal to any material object at distances of thousands of miles, and they can trigger explosive releases of energy that briefly outshine entire galaxies. The study of these extreme magnetic environments helps scientists understand the fundamental physics of magnetism under conditions that could never be replicated in terrestrial laboratories. Black holes, despite their reputation for consuming everything that comes near them, also generate powerful magnetic fields through the motion of charged particles in the superheated gas that spirals into them. These magnetic fields can accelerate jets of particles to nearly the speed of light, creating narrow beams of energy that extend for thousands of light years into space. The magnetic processes operating around black holes are thought to play crucial roles in regulating star formation throughout galaxies and in distributing heavy elements created in stellar cores across vast regions of space. On the largest scales, magnetic fields appear to thread through entire galaxies, influencing the formation of stars and the evolution of galactic structure. The Milky Way galaxy possesses a magnetic field that aligns roughly with the spiral arms, suggesting that magnetic forces play important roles in maintaining the galaxy's structure and in triggering the formation of new pole stars. These galactic magnetic fields, while incredibly weak by terrestrial standards, extend across such vast distances that their total energy content rivals that of all the starlight in the galaxy. Even larger magnetic structures have been detected spanning the voids between galaxies, creating a cosmic web of magnetism that extends throughout the observable universe. These intergalactic magnetic fields, while extremely weak, may have played important roles in the formation of the first galaxies and continue to influence the flow of matter through the universe today. The origin of these cosmic magnetic fields remains one of the greatest mysteries in astrophysics, with some theories suggesting they may be relics from the earliest moments after the Big Bang. The study of magnetic fields throughout the universe has revealed that magnetism is not just a curious property of certain materials or a useful tool for navigation, but a fundamental force that shapes the structure and evolution of the cosmos itself. From the dynamo operating in Earth's core to the magnetic engines powering distant quasars, the same basic physical principles govern magnetic phenomena across an enormous range of scales and environments. This cosmic perspective on magnetism helps us appreciate both the universality and the uniqueness of Earth's magnetic field. While magnetic fields are common throughout the universe, the specific configuration of Earth's magnetosphere, its stability over geological time, and its role in protecting our planet's atmosphere and biosphere make it a remarkable and perhaps rare phenomenon. The combination of factors that has allowed Earth to maintain a strong magnetic field for billions of years may be one of the key conditions that has made our planet suitable for the emergence and evolution of complex braid life. As we continue to explore the magnetic mysteries of the universe, new technologies are providing unprecedented insights into magnetic phenomena both near and far. Radio telescopes can map the magnetic fields of distant galaxies by detecting the polarized radio waves emitted by charged particles spiraling along magnetic field lines. Space-based observatories can measure the magnetic fields of other stars by observing how these fields affect the light emitted by stellar atmospheres. And increasingly sophisticated computer simulations are helping scientists understand how magnetic fields evolve and interact across cosmic time and space. The search for life beyond Earth has also highlighted the importance of understanding planetary magnetic fields. As astronomers discover thousands of exoplanets orbiting other stars, one of the key questions about each new world is whether it possesses a magnetic field capable of protecting any potential atmosphere and biosphere from the harmful effects of stellar radiation and cosmic rays. The presence or absence of magnetic fields may prove to be one of the most important factors determining which exoplanets are truly habitable and which are sterile worlds incapable of supporting life as we know it. Some of the most Earth-like exoplanets discovered so far orbit red dwarf stars, which are smaller and cooler than our Sun, but much more magnetically active. These red dwarf stars can produce magnetic storms and stellar flares far more powerful than anything our Sun generates, creating challenging environments for any planets that orbit them. Whether rocky planets around red dwarf stars could maintain magnetic fields strong enough to withstand such intense stellar activity is one of the key questions in assessing the habitability of these potentially life-bearing worlds. The study of Earth's magnetic field thus serves as both a foundation for understanding magnetism throughout the universe and a baseline for evaluating the habitability of other worlds. Every measurement of Earth's magnetic field, every insight into the dynamo process operating in our planet's core, and every discovery about how our magnetosphere interacts with the solar wind contributes to our broader understanding of how magnetic fields work and how they influence the potential for life throughout the cosmos. Recent advances in laboratory physics are also providing new insights into the magnetic processes operating in planetary cores and stellar interiors. Powerful lasers can now create conditions of temperature and pressure similar to those found deep within planets, allowing scientists to study how magnetic fields are generated and maintained under extreme B conditions. These experiments are revealing new aspects of the dynamo process and helping to refine theoretical models of planetary magnetism. High-performance computing has revolutionized the study of magnetic fields by enabling scientists to create detailed simulations of dynamo processes that would be impossible to study experimentally. These computer models can simulate the complex fluid motions in planetary cores over thousands of years, revealing how magnetic fields evolve and occasionally reverse. While these simulations are still far from perfect, they are beginning to reproduce many of the observed characteristics of Earth's magnetic field and are providing valuable insights into the physical processes that govern planetary magnetism. The development of new materials with exotic magnetic properties is also opening up new possibilities for understanding and manipulating magnetic fields. Superconductors, which can carry electrical currents without resistance, can generate extremely powerful magnetic fields and may provide clues about how magnetic fields behave under conditions very different from those found in planetary cores. Metamaterials with engineered magnetic properties are revealing new ways that magnetic fields can be controlled and shaped, potentially leading to applications in everything from medical imaging to space propulsion. Quantum mechanics is providing another new perspective on magnetism, revealing that magnetic fields can have properties that are fundamentally different from what classical physics would predict. Quantum magnetic systems can exhibit phenomena like entanglement and superposition that have no classical analogues, and these quantum effects may play important roles in some types of magnetic systems found in nature. The intersection between quantum physics and magnetism is an active area of research that may lead to new technologies and new insights into the fundamental nature of magnetic fields. As our understanding of magnetism continues to evolve, we are beginning to appreciate that magnetic fields are not just passive features of the universe, but active agents that influence the formation Evolution of cosmic structures. Magnetic fields can trigger the collapse of gas clouds to form new stars, regulate the rate at which matter falls into black holes, and influence the paths followed by cosmic ray particles as they travel through space. In this sense, magnetism is as fundamental to the workings of the universe as gravity or the strong nuclear force. The story of Earth's magnetic field is thus part of a much larger story about magnetism throughout the cosmos. The same physical principles that govern the dynamo in Earth's core also operate in the hearts of distant stars, the centers of other planets, and the vast spaces between galaxies. By studying Earth's magnetic field in detail, we gain insights not just into our own planet, but into the fundamental nature of magnetism itself and its role in shaping the universe around us. This cosmic perspective also reminds us of our connection to the broader universe and the deep relationships that link our planet to the stars. The iron atoms that flow in Earth's core and generate our magnetic field were forged in the nuclear furnaces of ancient stars and scattered into space when those stars exploded as supernovas. The magnetic field that protects us today is thus built from the ashes of stellar death and powered by processes that operate throughout the cosmos. The charged particles that create the aurora when they interact with Earth's magnetic field originate in our Sun's nuclear core and carry with them a tiny fraction of the star's magnetic field. When we observe the northern or southern lights dancing across the polar sky, we are witnessing a direct interaction between Earth's magnetic field and the magnetic environment of our entire solar system. In this sense, the aurora serve as visible reminders of our planet's place in the larger magnetic web that connects all the worlds orbiting our Sun. As we look toward the future, the study of Earth's magnetic field will undoubtedly continue to reveal new insights into both our own planet and the universe beyond. New missions to other planets will help us understand how magnetic fields evolve and what factors determine whether a world can maintain long-term magnetic protection. Advanced telescopes will allow us to study the magnetic fields of exoplanets directly, helping us assess their potential habitability and understand how common Earth-like magnetic environments might be throughout CAS. The galaxy. The development of new technologies may also allow us to influence or even create magnetic fields in ways that were previously impossible. Proposals for magnetic shields to protect spacecraft during long-duration missions to Mars and beyond represent early steps toward engineering magnetic protection for human exploration of the solar system. While such technologies are still largely theoretical, they demonstrate how our understanding of natural magnetic phenomena could inspire new approaches to the challenges of space exploration and planetary cruise. Protection. The magnetic field that surrounds our planet today has been our constant companion throughout the entire history of life on Earth. It protected the first primitive organisms as they evolved in ancient oceans, shielded the ancestors of all complex life as they colonized the land, and continues to guard our biosphere against the hostile BRAV, radiation environment of space. This magnetic guardian has witnessed the rise and fall of countless species, the dramatic changes in Earth's climate and geography, and the recent emergence of human civilization with its growing understanding of the magnetic forces that have made our existence possible. In contemplating the hidden history of Earth's magnetic field, we are reminded that we are part of an ongoing story that extends far beyond our brief individual lives, or even our species' short time on Double. This planet. The magnetic field that protects us today is the product of processes that began when Earth first formed and will continue long after our current era has passed into geological history. We are temporary custodians of a world that has been shaped by invisible forces operating on timescales we can barely comprehend, forces that connect us to the deepest mysteries of our planet and the cosmos beyond. The journey through Earth's magnetic history reveals the profound interconnectedness of all natural phenomena, from the smallest atomic interactions to the largest cosmic structures. The magnetic field that guides a compass needle and paints the aurora across the polar sky is generated by the same fundamental forces that power the stars and shape the evolution of galaxies. In understanding Earth's magnetism, we gain insight into the workings of the universe itself and our place within the vast cosmic web of magnetic forces that extends from the center of our planet to the edge of the observable universe. As this exploration of Earth's magnetic field draws to a close, we are left with a deeper appreciation for the invisible forces that surround us and the remarkable planet we call home. The magnetic field that has protected life for billions of years continues its ancient vigil, a testament to the enduring power of the natural forces that govern our world. In its steady presence, we find both humility before the vastness of cosmic processes and wonder at the delicate balance of conditions that has allowed consciousness to emerge and contemplate its own magnetic origins. The hidden history of Earth's magnetic field is ultimately a story about the dynamic, interconnected nature of our universe and our place within it. From the molten iron churning in our planet's core to the charged particles streaming from distant stars, from the compass stones that guided ancient navigators to the satellite technology that monitors our magnetic environment today, this history reveals the threads that connect us to the cosmos and the invisible forces that continue to shape our destiny among the stars. As we stand at the threshold of a new era in our understanding of Earth's magnetic field, we find ourselves equipped with tools and knowledge that would have seemed magical to the ancient peoples who first marveled at the mysterious properties of lodestones. Sophisticated satellites circle our planet, continuously monitoring the subtle variations in magnetic field strength and direction that provide clues to the complex processes operating deep within Earth's core. Ground-based observatories around the world maintain constant vigil, recording magnetic fluctuations that occur on timescales ranging from seconds to decades, building a comprehensive picture of how our magnetic environment responds to both internal changes and external influences from space. The data flowing from these monitoring systems reveal that Earth's magnetic field is far more dynamic and variable than early investigators could have imagined. While the overall dipolar structure of the field remains relatively stable on human timescales, closer examination shows that the field is in constant motion, with magnetic patterns drifting westward around the globe at rates of several miles per year. This westward drift, first noticed in historical compass records from the 17th century, reflects the rotation of fluid structures within Earth's liquid iron core, providing direct evidence of the dynamic processes that generate our planet's magnetism. Superimposed on this slow westward drift are rapid fluctuations that occur on much shorter timescales. Magnetic storms triggered by interactions between Earth's magnetosphere and the solar wind can cause the magnetic field to fluctuate dramatically over periods of hours or days. During intense magnetic storms, compass needles may deviate significantly from their normal orientations, and the aurora may be visible at latitudes far from their usual polar domains. These events demonstrate the intimate connection between Earth's magnetic field and the constantly changing space environment that surrounds our planet. More subtle but equally important are the gradual changes in magnetic field strength and geometry that unfold over years and decades. Detailed analysis of historical magnetic observations reveals that certain regions of Earth's magnetic field are strengthening while others are weakening. creating complex patterns of change that reflect the evolving fluid motions in the planet's core. The South Atlantic anomaly, where the magnetic field is particularly weak, has been expanding and intensifying for decades, while new regions of magnetic weakness have begun to appear in other parts of the world. These ongoing changes in Earth's magnetic field carry profound implications for our technological civilization. The global positioning system, which relies on signals from satellites orbiting 20,000 kilometers above Earth's surface, must account for magnetic field variations that can affect the propagation of radio waves through the ionosphere. Airlines routinely adjust flight paths over the polar regions to account for changing magnetic conditions that can interfere with navigation systems and increase radiation exposure for crew and passengers. Power grid operators monitor space weather forecasts and magnetic field predictions to prepare for geomagnetic storms that can induce damaging electrical currents in transmission lines. The vulnerability of modern technology to magnetic field variations has spurred increased investment in space weather research and magnetic field monitoring. Scientists now recognize that understanding and predicting magnetic field changes is not just a matter of scientific curiosity, but a practical necessity for maintaining the technological infrastructure on which our society depends. This has led to the development of increasingly sophisticated models of the geodynamo process and more accurate methods for forecasting magnetic field behavior on timescales ranging from days to decades. One of the most significant recent advances in magnetic field research has been the development of three-dimensional computer simulations of the geodynamo process. These models, running on some of the world's most powerful supercomputers, can simulate the complex fluid motions in Earth's liquid iron core with unprecedented detail and accuracy. By incorporating the effects of Earth's rotation, the planet's cooling history, and the complex interactions between thermal and compositional convection, these simulations are beginning to reproduce many of the observed characteristics of Earth's magnetic field, including its strength, geometry, and temporal variations. Perhaps most remarkably, some of these computer models have successfully simulated magnetic field reversals, reproducing the complex sequence of events that leads to a complete flip in the magnetic field's polarity. These simulated reversals begin with a gradual weakening of the dipolar field, followed by the growth of more complex magnetic structures with multiple poles scattered around the globe. The simulated magnetic field fluctuates chaotically between different configurations before finally settling into the opposite polarity, a process that unfolds over several thousand years in the model, consistent with observations of real magnetic reversals preserved in the geological record. These computational breakthroughs have provided new insights into the physical mechanisms that control magnetic field generation and reversal. The simulations suggest that magnetic reversals are triggered by specific patterns of fluid flow in the core, particularly interactions between rising plumes of hot iron and the planet's rotation. When these interactions reach certain critical thresholds, they can destabilize the existing magnetic field configuration and initiate the complex reorganization process that leads to a reversal. The ability to simulate magnetic reversals in computer models has also allowed scientists to investigate what might happen to Earth's magnetic field in the future. While the chaotic nature of the geodynamo process makes long-term prediction extremely difficult, the models provide valuable insights into the types of changes that might occur and the timescales over which they might unfold. Some simulations suggest that the current weakening trend in Earth's magnetic field could continue for several more centuries before the field begins to recover, while others indicate that we might be approaching another magnetic reversal within the next few thousand years. The study of magnetic field variations on Mars and Venus has provided additional context for understanding Earth's magnetic evolution. Mars appears to have lost its global magnetic field early in its history, but detailed measurements by orbiting spacecraft have revealed that the planet retains localized magnetic fields in certain regions of its crust. These crustal magnetic anomalies, some of which are stronger than Earth's current magnetic field, preserve a record of Mars's ancient magnetosphere and provide clues about how planetary magnetic fields can be lost and partially preserved. Venus, despite being similar in size to Earth, shows no evidence of a current magnetic field, though some theoretical models suggest that it might have possessed magnetism in the past. The absence of a magnetic field on Venus may be related to the planet's extremely slow rotation, which occurs only once every 243 Earth days. This slow rotation may be insufficient to drive the convective motions necessary to sustain a dynamo process, illustrating how planetary rotation rate can influence magnetic field generation. The magnetic environments of the gas giant planets have revealed additional complexities in planetary magnetism that challenge our understanding of dynamo processes. Jupiter's magnetic field, generated by convection in a layer of metallic hydrogen under extreme pressure, operates according to principles that are fundamentally different from those governing terrestrial bassa magnetism. The rapid rotation of Jupiter, which completes one revolution in less than 10 hours, creates powerful Coriolis forces that organize the convective flows into distinct bands and zones, similar to the visible battery. Cloud patterns in the planet's atmosphere. Saturn's mysterious magnetic field alignment has prompted new theoretical investigations into how magnetic fields can maintain stable configurations under different planetary conditions. Recent studies suggest that Saturn's ring system may play a crucial role in stabilizing the planet's magnetic field. With electrical currents flowing between the rings and the planet's ionosphere creating feedback mechanisms that help maintain the field's unusual geometry. The discovery of magnetic fields around some of the solar system's moons has opened up entirely new areas of research into small-body magnetism. Ganymede's internally generated magnetic field appears to be driven by convection in its subsurface ocean, suggesting that liquid water can serve as an electrical conductor under the right conditions. This discovery has profound implications for the search for life beyond Earth, as magnetic fields generated by subsurface oceans could provide protection for any organisms that might exist in these hidden decal. Aquatic environments. Europa's induced magnetic field, created by the interaction between Jupiter's powerful magnetosphere and the Moon's conducting ocean, provides some of our best evidence for the existence of liquid water beneath Europa's icy surface. The strength and variability of this induced field allow scientists to estimate the depth and salinity of Europa's ocean, information that is crucial for assessing the Moon's potential habitability. Similar magnetic signatures have been detected around other icy moons, suggesting that subsurface oceans may be common features throughout the outer solar system. The study of magnetic fields in meteorites and lunar samples has revealed that even small bodies can generate magnetic fields under certain conditions. Some meteorites show evidence of having been magnetized by magnetic fields that existed in the early solar system, providing insights into the magnetic environment that surrounded the forming planets billions of Cash-Shen years ago. Lunar rocks returned by the Apollo missions contain magnetic signatures that suggest the Moon may have possessed a magnetic field early in its history, possibly generated by a now solidified iron core. Recent advances in paleomagnetic research have extended our knowledge of Earth's magnetic field history much further back in time than previously possible. New analytical techniques can extract magnetic information from increasingly ancient rocks, revealing that Earth has maintained some form of magnetic field for at least 3.5 billion years, and possibly can much longer. This ancient magnetic record provides crucial constraints on models of early Earth evolution and helps scientists understand how the geodynamo process has evolved over geological time. The discovery of magnetic field signatures in some of the oldest rocks on Earth suggests that our planet's magnetic field may have been present almost from the very beginning of Earth's history. This early magnetism would have been crucial for protecting the primitive atmosphere from solar wind erosion, creating the stable environmental conditions necessary for the emergence of life. Without this ancient magnetic protection, Earth might have suffered the same fate as Mars, losing its atmosphere and becoming a cold, dry world incapable of supporting the complex chemistry required for biological processes. The relationship between Earth's magnetic field and the evolution of life remains an active area of research, with scientists investigating whether magnetic field variations might have influenced evolutionary processes over geological time. Some studies have suggested correlations between magnetic reversal events and certain extinction or evolutionary transition events, though establishing definitive causal relationships has proved challenging. The increased cosmic radiation that reaches Earth's surface during magnetic reversals could potentially affect genetic mutation rates or atmospheric chemistry in ways that might influence biological evolution. More immediate concerns focus on how current and future magnetic field changes might affect human health and technology. Astronauts and airline crews who spend significant time at high altitudes or in space are already exposed to increased cosmic radiation due to reduced magnetic field protection in certain regions. The South Atlantic anomaly, where Earth's magnetic field is particularly weak, poses known risks to satellites and spacecraft, requiring special precautions for missions that pass through this region. The potential health effects of magnetic field variations on the general population remain largely unknown, though some researchers have investigated possible connections between geomagnetic activity and various biological processes. While Earth's magnetic field is far too weak to have direct effects on human physiology, some studies have suggested that magnetic field fluctuations might influence circadian rhythms or other biological cycles that are sensitive to environmental changes. However, such effects, if they exist at all, appear to be very subtle and difficult to detect against the background of other environmental influences. The growing recognition of our dependence on Earth's magnetic field has led to increased international cooperation in magnetic field research and monitoring. The World Magnetic Model, updated every 5 years by a collaboration between American and British scientists, provides the standard reference for magnetic field values used in navigation systems worldwide. This model must account for the continuous changes in Earth's magnetic field, requiring constant updates based on the latest satellite and ground-based observations. Recent versions of the World Magnetic Model have required more frequent updates than in the past, reflecting the accelerating pace of magnetic field change in certain regions. The rapid movement of the North Magnetic Pole towards Siberia has been particularly challenging for navigation systems, requiring emergency updates to ensure that compass-based navigation remains accurate. These rapid changes highlight the dynamic nature of Earth's magnetic field and the importance of continuous monitoring to maintain technological systems that depend on magnetic field information. The future of magnetic field research promises even more detailed understanding of the processes that generate and maintain planetary magnetism. New satellite missions are being planned that will provide unprecedented resolution and accuracy in magnetic field measurements, allowing scientists to study magnetic field variations on increasingly fine spatial and temporal scales. These missions will help resolve long-standing questions about the detailed structure of Earth's magnetic field and its relationship to the fluid motions in the planet's core. Ground-based magnetic observatories are also being upgraded with more sensitive instruments and better global coverage, particularly in remote regions where magnetic field monitoring has historically been sparse. The combination of satellite and ground-based observations is providing an increasingly complete picture of Earth's magnetic environment and its variations over time. This comprehensive monitoring network is essential for understanding how Earth's magnetic field responds to changes in the solar wind and how internal processes in the core influence the field's long-term evolution. Laboratory experiments using powerful lasers and magnetic field generators are beginning to recreate some of the extreme conditions that exist in planetary cores, allowing scientists to study dynamo processes under controlled conditions. These experiments, while still far from reproducing the full complexity of planetary magnetism, are providing valuable insights into the fundamental physics of magnetic field generation and the material properties that influence dynamo efficiency. The development of new materials with exotic magnetic properties is also opening up new possibilities for technological applications inspired by natural magnetic phenomena. Superconducting materials that can maintain powerful magnetic fields without energy input are being investigated for applications ranging from medical imaging to magnetic levitation transportation. While such technologies are still largely experimental, they demonstrate how our understanding of natural magnetism continues to inspire new approaches to technological challenges. The search for life beyond Earth has made understanding planetary magnetic fields a priority for astrobiology research. As we discover more exoplanets orbiting other stars, one of the key questions about each new world is whether it possesses a magnetic field capable of protecting any potential atmosphere and biosphere. The techniques being developed to study Earth's magnetic field in detail are also being adapted to search for magnetic fields around exoplanets, though such measurements remain at the limits of current observational capabilities. Some of the most promising targets for exoplanet magnetic field detection are close in planets orbiting red dwarf stars, where the intense stellar magnetic activity might induce detectable magnetic signatures in planetary atmospheres. Radio telescopes are being used to search for the characteristic emissions that would be produced by charged particles interacting with exoplanetary magnetic fields, similar to the radio emissions detected from Jupiter and other magnetized planets in our solar system. The study of stellar magnetic activity is also providing insights into how planetary magnetic fields might evolve over time. Young stars tend to be much more magnetically active than older stars like our Sun, producing powerful magnetic storms and stellar winds that could strip away planetary atmospheres or trigger intense auroral activity on any orbiting worlds. Understanding how stellar magnetic activity changes over time is crucial for assessing the long-term habitability of exoplanetary systems and the role that magnetic protection plays in allowing life to emerge and evolve. As our knowledge of Earth's magnetic field continues to expand, we are gaining a deeper appreciation for the delicate balance of conditions that has allowed our planet to maintain its magnetic protection for billions of years. The size of Earth's core, the rate of planetary cooling, the chemical composition of the core materials, and countless other factors have all contributed to creating the specific conditions necessary for sustained magnetic field generation. Small changes in any of these factors might have led to a very different magnetic history and a very different Earth. This understanding of the factors that control planetary magnetism is informing our search for other potentially habitable worlds and helping us appreciate the remarkable circumstances that have made Earth suitable for life. The magnetic field that protects us is not a given feature of rocky planets, but rather the result of a complex interplay of physical and chemical processes that must align in specific ways to create lasting magnetic protection. The ongoing study of Earth's magnetic field also serves as a reminder of the interconnected nature of all planetary processes. The magnetic field generated in Earth's core influences atmospheric chemistry through its effects on cosmic ray penetration. Changes in the magnetic field affect the radiation environment in space, influencing everything from satellite operations to the evolution of life itself. The same fluid motions that generate the magnetic field also drive other geological processes, creating connections between magnetism and phenomena as diverse as continental drift and volcanic activity. As we look toward the future, the story of Earth's magnetic field continues to unfold with each new measurement and each new discovery. The satellites currently orbiting our planet are documenting magnetic field changes in real time, creating an unprecedented record of how our magnetic environment evolves on human timescales. These observations are not just of scientific interest, but are becoming increasingly important for practical applications as our technological civilization becomes more dependent on systems that are vulnerable to magnetic field variations. The challenges facing magnetic field research in the coming decades include developing better theoretical models of the geodynamo process, improving our ability to predict magnetic field changes, and understanding the connections between Earth's magnetic field and other planetary systems. New computational techniques and more powerful computers will enable more realistic simulations of core dynamics, while advances in observational technology will provide more detailed measurements of magnetic field structure and evolution. International collaboration will continue to be essential for advancing our understanding of Earth's magnetic field, as the global nature of magnetic phenomena requires coordinated observations, theoretical efforts that span national boundaries. The sharing of data and expertise among researchers around the world has been crucial for progress in magnetic field research and will become even more important as the complexity and scope of magnetic field studies continue to expand. The story of Earth's magnetic field is ultimately a story about discovery and understanding, about human curiosity driving us to investigate invisible forces that shape our world in profound ways. From the ancient Greeks who first noticed the strange properties of magnetic stones, to the modern scientists who monitor our planet's magnetic environment from space, each generation has built upon the discoveries of those who came before, gradually revealing the hidden workings of one of Earth's most fundamental features. In contemplating this long history of discovery, we could appreciate both how far our understanding has advanced and how many mysteries remain to be solved. The basic physics of magnetic field generation is now well understood, yet predicting exactly how Earth's magnetic field will behave in the future remains beyond our current capabilities. We know that magnetic reversals occur, but we cannot predict when the next one might happen. We understand that Earth's magnetic field is weakening in some regions and strengthening in others, but we cannot say with certainty whether these changes represent normal fluctuations or the beginning of a major transition. These remaining uncertainties serve not as limitations, but as invitations for future discovery. Each unanswered question about Earth's magnetic field represents an opportunity for new insights and new understanding. The next generation of magnetic field researchers will have access to tools and techniques that we can barely imagine today, just as today's scientists have capabilities that would have seemed magical to their predecessors. The magnetic field that surrounds our planet and protects our biosphere is both a local phenomenon generated by processes specific to Earth's interior and a universal one reflecting physical principles that can operate throughout the cosmos. In studying Earth's magnetism, we gain insights not only into our own world but into the workings of magnetic fields everywhere, from the smallest planetary bodies to the largest galactic structures. This dual nature of Earth's magnetic field, both unique and universal, makes its study particularly rewarding for anyone interested in understanding our place in the cosmos. The same magnetic forces that guide a compass needle and create the aurora also power the most energetic phenomena in the universe and play crucial roles in the formation and evolution of stars, planets, and galaxies. By understanding Earth's magnetic field, we gain a key to unlocking magnetic mysteries throughout the universe. The hidden history of Earth's magnetic field thus serves as both a scientific chronicle and a philosophical meditation on the nature of discovery and understanding. It reminds us that the universe is full of invisible forces and hidden connections that shape our existence in ways we are only beginning to comprehend. The magnetic field that has protected life on Earth for billions of years continues to reveal new secrets and new surprises, ensuring that the story of terrestrial magnetism will continue to unfold for generations to come. As we conclude this extended journey through the hidden history of Earth's magnetic field, we are left with a profound sense of wonder at the invisible forces that surround us and the remarkable planet we inhabit. The magnetic field that guides migrating animals, protects astronauts in orbit, and paints the aurora across polar skies represents one of the most fundamental and enduring features of our world, a testament to the dynamic processes that have shaped Earth throughout its long history. In the steady presence of this magnetic guardian, we find both security and inspiration. Security in knowing that powerful forces continue to protect our biosphere from the harsh environment of space, and inspiration in contemplating the deep connections that link our planet to the broader cosmos. The story of Earth's magnetic field is ultimately our own story, the tale of a world where invisible forces have created the conditions necessary for life, consciousness, and the ongoing quest to understand our place in the vast magnetic web that connects all things in the universe. The magnetic field that envelops our planet operates according to principles that extend far beyond the boundaries of Earth itself, connecting us to physical processes that govern the behavior of matter and energy throughout the cosmos. Every iron atom in Earth's core carries within it the memory of its stellar birth, forged in the nuclear furnace of an ancient star and scattered into space when that star exhausted its fuel and exploded in a supernova. The magnetic properties of these iron atoms, which enable them to respond to and generate magnetic fields, are consequences of quantum mechanical principles that operate at the smallest scales of reality, yet manifest themselves in planetary phenomena visible from space. The electrons orbiting within each iron atom possess a property called spin, a quantum characteristic that makes each electron behave like a tiny magnet. Under normal conditions, these atomic magnets point in random directions, their effects cancelling each other out. But under the extreme conditions found in Earth's core, temperatures exceeding those on the Sun's surface, and pressures millions of times greater than atmospheric pressure, these atomic magnets can become aligned, creating the macroscopic magnetic properties that drive the geodynamo process. This quantum foundation of magnetism reveals one of the most remarkable aspects of Earth's magnetic field. It represents a bridge between the smallest and largest scales of physical reality. The quantum mechanical properties of individual atoms, operating according to principles that seem alien to our everyday experience, combine to create planetary-scale phenomena that influence everything, from navigation to the aurora. In this sense, Earth's magnetic field serves as a tangible demonstration of how quantum mechanics shapes the macroscopic world in which we live. The fluid ion that generates Earth's magnetic field exists in a state that would be impossible to maintain under normal surface conditions. At the temperatures and pressures found in the core, iron becomes a liquid metal with properties unlike any material we encounter in everyday life. This liquid iron conducts electricity far more efficiently than copper wire, allowing electrical currents to flow through it with minimal resistance. These currents, driven by the complex motions of the fluid ion, can persist for thousands of years, creating the sustained electrical activity necessary to maintain Earth's magnetic field. The convective motions that drive these electrical currents are powered by heat flowing from the very center of Earth toward the surface. Some of this heat is primordial, left over from the violent collisions that formed our planet 4.5 billion years ago. But much of it comes from the radioactive decay of elements like uranium, thorium, and potassium scattered throughout Earth's interior. These radioactive elements, themselves created in the nuclear furnaces of ancient stars, continue to release energy billions of years after their formation, providing the thermal engine that drives the geodynamo process. The geometry of Earth's magnetic field reflects the complex interplay between these thermal driving forces and the constraints imposed by planetary rotation. The Coriolis effect, which arises from Earth's daily spin, organizes the convective flows in the core into columnar structures aligned with the rotation axis. These thermal columns, invisible rivers of flowing iron extending through the entire depth of the liquid core, create the predominantly dipolar structure of Earth's magnetic field, while also generating the smaller scale magnetic features that cause regional variations in field strength and direction. Recent advances in seismology have begun to reveal the three-dimensional structure of these convective flows through their effects on seismic waves passing through the core. Earthquake waves traveling through regions of upwelling hot iron move slightly faster than those passing through areas of, quote, downwelling cool iron, creating subtle variations in travel time that can be detected by sensitive seismometers around the world. These seismological observations provide a unique window into the fluid motions that generate Earth's magnetic field, allowing scientists to map the invisible currents flowing nearly 3,000 miles beneath our feet. The magnetic field lines that emerge from Earth's core and extend into space follow paths that are constantly evolving in response to changes in the core's fluid motions. Near Earth's surface, these field lines create the familiar pattern of a dipole magnet, emerging from the southern hemisphere, arcing through space, and converging toward the northern hemisphere. But this simple description masks a complex three-dimensional structure that includes magnetic field lines that loop through the core itself, creating a tangled web of magnetic connections throughout Earth's interior. The interaction between Earth's magnetic field and the solar wind creates one of the most dynamic boundaries in our solar system. The magnetopause, where Earth's magnetic field meets the solar wind, is not a solid barrier but a constantly shifting interface where magnetic and plasma forces compete for dominance. During periods of intense solar activity, the solar wind can compress Earth's magnetosphere so severely that the magnetopause moves to within a few thousand miles of our planet's surface, dramatically altering the paths followed by charged particles and potentially affecting satellite operations and radio communications. Within the magnetosphere, charged particles from the solar wind become trapped along magnetic field lines, creating the Van Allen radiation belts that surround Earth like invisible donuts of energetic heat. Particles. These radiation belts, discovered during the early space age, represent regions where Earth's magnetic field is so effective at trapping charged particles that dangerous levels of radiation accumulate. Spacecraft traveling through these regions must be specially shielded to protect their electronic systems from radiation damage, and astronauts venturing beyond low Earth orbit must time their missions to minimize exposure to these hazardous zones. The dynamics of the magnetosphere also create a complex system of electrical currents flowing through space around Earth. These currents, carried by charged particles moving along magnetic field lines, can reach intensities of millions of amperes, rivaling the current flow in major power transmission lines. During magnetic storms, these space currents can fluctuate rapidly, inducing secondary currents in Earth's conducting surface layers and potentially overloading power grids and disrupting electronic communications. The study of these magnetospheric currents has revealed that Earth's magnetic environment is intimately connected to the Sun's magnetic activity through a process called magnetic reconnection. When magnetic field lines from the Sun, carried outward by the solar wind, encounter Earth's magnetic field lines in just the right configuration, they can suddenly snap together and reorganize themselves, releasing enormous amounts of energy in the process. This magnetic reconnection powers many of the most dramatic space weather events, from intense auroral displays to the magnetic storms that can disrupt technological systems. Understanding magnetic reconnection has become crucial for predicting space weather and protecting technological infrastructure from magnetic disturbances. Scientists have discovered that this same process operates throughout the universe, from the solar corona where it drives solar flares, to the magnetospheres of other planets, to the vast magnetic fields that thread through galaxies. In studying magnetic reconnection around Earth, researchers are gaining insights into one of the most fundamental processes governing the behavior of magnetized plasmas throughout the cosmos. The aurora that result from these magnetospheric processes represent perhaps the most visible and beautiful manifestation of Earth's magnetic field in action. The colors of the aurora depend not only on the types of atmospheric gases being excited by incoming particles, but also on the energy of those particles and the altitude at which collisions occur. High-energy particles can penetrate deeper into the atmosphere, exciting different atmospheric constituents and creating the full spectrum of auroral colors from deep red to vibrant green to rare blue, purple. Recent research has revealed that auroral displays can be far more complex and structured than the simple curtains of light visible to casual observers. High-resolution cameras and radar systems have detected fine-scale auroral features called auroral arcs, which can be only a few hundred meters wide yet extend for hundreds of kilometers across the sky. These narrow arcs often display rapid flickering and pulsating behavior, reflecting turbulent processes occurring along magnetic field lines far above Earth's surface. The aurora also serve as natural laboratories for studying plasma physics under conditions that cannot be replicated in terrestrial experiments. The interactions between charged particles and magnetic fields that create auroral light follow the same physical principles that govern the behavior of plasma in fusion reactors, stellar atmospheres, and the vast spaces between galaxies. By studying auroral phenomena in detail, scientists gain insights into plasma physics that have applications ranging from developing clean energy sources to understanding the most energetic events in the universe. Modern aurora research has also revealed connections between auroral activity and other atmospheric phenomena. Auroral heating can affect atmospheric circulation patterns at high altitudes, potentially influencing weather systems at lower altitudes through complex coupling mechanisms. Some studies have suggested that intense auroral activity might even affect the formation of clouds in the upper atmosphere, creating subtle but measurable changes in Earth's radiation balance and climate. The magnetic field's influence on Earth's atmosphere extends beyond its role in creating aurora and protecting against charged particle bombardment. The geomagnetic field affects the penetration of cosmic rays into the atmosphere, with stronger magnetic fields deflecting more cosmic rays and weaker fields allowing more to penetrate. This cosmic ray modulation can influence atmospheric chemistry, particularly the production of radioactive isotopes like carbon-14 and beryllium-10 that are created when cosmic rays interact with atmospheric nuclei. These cosmogenic isotopes serve as natural recorders of past magnetic field strength, preserved in ice cores, tree rings, and sediment layers that extend back thousands of years. By measuring the concentrations of these isotopes in natural archives, scientists can reconstruct the history of Earth's magnetic field with much greater temporal resolution than is possible using the magnetic Kappa wall, signatures preserved in rocks. This cosmogenic isotope record has revealed that Earth's magnetic field has fluctuated significantly over the past few thousand years, with periods of particularly weak field strength occurring during some historical intervals. The relationship between magnetic field strength and cosmic ray penetration also has implications for understanding past climate changes. Cosmic rays can influence cloud formation through their effects on atmospheric ionization, potentially creating links between magnetic field variations and climate variability. While these connections remain controversial and difficult to quantify, they illustrate the complex ways in which Earth's magnetic field can influence environmental conditions far beyond its direct Electromagnetic effects. The magnetic field also plays a role in the migration patterns of many animal species that use Earth's magnetic field for navigation. Birds, sea turtles, salmon, and many other animals possess biological magnetometers that allow them to sense the direction and intensity of the magnetic field, using this information to navigate across vast distances during migration. The exact mechanisms by which these biological compass systems work remain active areas of research, with studies suggesting that they may involve specialized cells containing magnetite crystals or quantum mechanical processes occurring in certain proteins. The sensitivity of these biological magnetometers is remarkable, often exceeding the precision of human-made instruments. Some migrating birds can detect magnetic field variations as small as a few nanotesla, changes so subtle that they would be undetectable without sophisticated electronic equipment. This extraordinary sensitivity allows these animals to navigate using magnetic landmarks and to compensate for the gradual changes in magnetic declination that occur as they travel across larger distances. Research into animal magnetoception has also revealed that many species can sense not just the direction of the magnetic field, but also its inclination and intensity, creating a three-dimensional magnetic map that provides remarkably precise positional information. This magnetic sense appears to be integrated with other navigation systems, including celestial navigation and landmark recognition, creating redundant guidance systems that ensure reliable navigation, even under challenging conditions. The study of animal magnetoception has practical implications for understanding how magnetic field changes might affect wildlife populations. Rapid changes in magnetic field strength or direction, such as those that might occur during a magnetic reversal, could potentially disrupt migration patterns and affect the survival of species that depend on magnetic Navigation. While animals have presumably survived past magnetic reversals throughout evolutionary history, the combination of rapid magnetic field changes with other environmental stresses might pose new challenges for wildlife conservation. The influence of Earth's magnetic field extends even to human activities in ways that are often invisible to us. The magnetic field affects the trajectories of charged particles in the upper atmosphere, influencing the formation and behavior of the ionosphere, the electrically conducting layer that makes long-distance radio communication possible. Changes in magnetic field strength and geometry can alter ionospheric conditions, affecting the propagation of radio waves and potentially disrupting communication systems that depend on ionospheric umbris. Reflection. The magnetic field also influences the formation of the radiation belts that surround Earth, which in turn affect the design and operation of satellites and spacecraft. Engineers must carefully consider the radiation environment when designing satellite systems, choosing materials and components that can withstand the harsh conditions found in Earth's magnetosphere. The gradual changes in Earth's magnetic field over time mean that the radiation environment is also evolving, requiring ongoing updates to spacecraft design criteria and mission planning procedures. Ground-based technology is also affected by magnetic field variations through the phenomenon of electromagnetic induction. When the magnetic field changes rapidly, as it does during magnetic storms, these changes induce electrical currents in conducting materials on Earth's surface, including power lines, pipelines, and railroad tracks. These induced currents can overload electrical systems, causing power outages and equipment damage. The vulnerability of modern electrical infrastructure to magnetic disturbances has led to increased investment in space weather monitoring and the development of protective systems to mitigate the effects of magnetic ET storms. The economic impact of magnetic field variations on modern technology is substantial and growing as our society becomes increasingly dependent on electronic systems. Power grid operators routinely factor space weather forecasts into their operational decisions, sometimes preemptively reducing power loads or reconfiguring transmission networks to minimize vulnerability to magnetically induced currents. Airlines adjust flight routes and schedules to account for increased radiation exposure and communication disruptions during magnetic storms. Satellite operators must continuously monitor the space environment and sometimes place their spacecraft in protective modes during periods of intense magnetic activity. The insurance industry has also begun to recognize the risks posed by extreme magnetic events, developing new models to assess the potential costs of widespread technological disruptions caused by severe toisons, magnetic storms. These economic analyses suggest that a major magnetic storm similar to the Carrington event of 1859, which occurred before the widespread deployment of electronic technology, could cause trillions of dollars in damage to modern infrastructure and take years to fully repair. This growing awareness of our technological vulnerability to magnetic disturbances has spurred increased investment in space weather research and the development of more resilient technological systems. Scientists are working to improve our ability to predict magnetic storms and their effects on technological infrastructure, while engineers are developing new techniques for protecting electronic systems from magnetic disturbances. International cooperation in space weather monitoring has also expanded, with organizations around the world sharing data and coordinating responses to magnetic threats. The study of Earth's magnetic field continues to reveal new aspects of this fundamental planetary feature with each advancement in observational and theoretical capabilities. Modern satellite missions can measure magnetic field variations with precision measured in fractions of a nanotesla, revealing subtle changes that would have been completely undetectable just a few decades ago. These high-precision measurements are providing unprecedented insights into the detailed structure of the magnetic field and its evolution over time. Ground-based magnetic observatories equipped with state-of-the-art instrumentation are also contributing to our understanding of magnetic field behavior on multiple timescales. Some observatories have been operating continuously for more than a century, providing long-term records of magnetic field changes that are essential for understanding the natural variability of Earth's magnetic environment. These historical records are particularly valuable for calibrating theoretical models of the geodynamo process and for placing current magnetic field changes in proper historical context. The integration of satellite and ground-based observations with increasingly sophisticated computer models is creating a more complete picture of Earth's magnetic field than has ever been possible before. These comprehensive datasets are revealing new aspects of magnetic field behavior, from rapid fluctuations that occur over minutes and hours to gradual trends that unfold over decades and centuries. The combination of observational data and theoretical modeling is also improving our understanding of the physical processes that control magnetic field generation and evolution. Looking toward the future, the study of Earth's magnetic field will undoubtedly continue to evolve as new technologies and techniques become available. Quantum sensors that exploit quantum mechanical principles to achieve unprecedented sensitivity are being developed for magnetic field measurements, potentially allowing the detection of magnetic variations that are currently beyond our observational capabilities. These quantum magnetometers could revolutionize our understanding of Earth's magnetic field by revealing subtle features and rapid changes that have previously been hidden from view. Artificial intelligence and machine learning techniques are also being applied to magnetic field research, helping scientists identify patterns and relationships in the vast datasets generated by modern bar monitoring systems. These computational approaches are particularly valuable for analyzing the complex, nonlinear behavior of the geodynamo system and for developing improved forecasting capabilities for magnetic field evolution. The exploration of other planets and moons in our solar system will continue to provide comparative context for understanding Earth's magnetic field and the factors that control planetary magnetism. Future missions to Mars, Venus, and the outer planets will carry increasingly sophisticated magnetic field instruments, allowing detailed studies of how planetary magnetic fields behave under different conditions. These comparative studies are essential for understanding which aspects of Earth's magnetic field are universal features of planetary magnetism and which are unique to our particular world. The search for exoplanets with magnetic fields is also likely to advance significantly in the coming decades as observational techniques improve and new instruments become available. Detecting magnetic fields around planets orbiting other stars remains extremely challenging with current technology. But several promising approaches are being developed that could make such measurements possible. In the near future, the discovery of magnetic fields around exoplanets would provide crucial information about their potential habitability and would extend our understanding of planetary magnetism to worlds far beyond our Temina. Solar System. As we continue to study Earth's magnetic field and its cosmic context, we are reminded of the profound interconnectedness of all natural phenomena. The magnetic field that protects our planet is intimately connected to processes occurring throughout the universe, from the quantum mechanical properties of individual atoms to the large-scale structure of galaxies. Understanding Earth's magnetism thus provides insights not only into our own world, but into the fundamental principles that govern the behavior of matter and energy throughout the cosmos. The story of Earth's magnetic field is ultimately a story about discovery and understanding. about the human quest to comprehend the invisible forces that shape our world and our place within it. From the ancient observations of magnetic stones to the sophisticated satellite measurements of today, each generation of investigators has built upon the work of their predecessors, gradually revealing the hidden mechanisms that generate and maintain our planet's magnetic protection. This ongoing process of discovery continues today, as new observations and theoretical advances reveal previously unknown aspects of Earth's magnetic field and its behavior. The magnetic field that has protected life on our planet for billions of years continues to hold secrets and surprises, ensuring that the study of terrestrial magnetism will remain an active and rewarding field of research for generations to come. In contemplating the hidden history of Earth's magnetic field, we gain not only scientific knowledge, but also a deeper appreciation for the remarkable circumstances that have made life possible on our planet. The invisible shield that surrounds us represents one of the most fundamental and enduring features of our world, a testament to the dynamic processes that continue to shape Earth's environment and its relationship to the broader cosmos.